So for this problem, we are asked what type of function and why. And so we have a little bit of work to do to make a decision about this function. The first thing we want to do is we want to use a numbering system other than the actual year. So we're going to make 2007 the first data point be our year 0. And then 2010 is 3 years later, so that would be year 3, year 6, year 9, and year 12. We are asked then to complete the table above. So first we're asked for the change in y. Change is subtraction, and so this means that we should take the y2 value and subtract the y1 value. And we're going to do this for each pair of data as we move through. We're then asked for the y ratio, and the ratio is division, and we always set up this ratio that it's the y2 divided by the y1 value. So I went ahead and did these and typed these all in rather than using up the video time to do that. So you see here the years all typed in that we talked through on the previous slide. You see that for change I did subtraction, for ratio I did division, and I have all of those. And I kept 4 decimal places or 5 so that you could see that they were not equal. They got to be pretty similar, but definitely not equal. So when I complete this table, the things that I am noticing here is that the change is not constant. And I'm also noticing that the y ratios are not constant. And so previously in class, when this was the case, we would have said it's approximately linear. But now we have more functions to pick from. So maybe it's approximately exponential, or maybe it's approximately logarithmic. So what we're going to do to figure out which function is to go out and create a graph of the data. So I'm going to go to my graphing calculator. I'm going to go into the stats section and hit enter to edit. I'm going to go up to the name, list 2, hit clear and enter to clear that. Same thing over here for list 1, go up to the name, hit clear and enter to get rid of those. In list 1, I am typing my renumbered years, so 0, 3, 6, 9, and 12. And then in list 2, I'm typing my y values, so 7, 8, 51, 9, 6, 1, 8, 11, 2, 12, 12, 6, 30, and 14, 2, 34. All right, so I got all my data in there. Before I move away from my data, I want to take a look and think through what kind of window I want. So I always want my window to capture my data, give me a little room. So list 1, I think I'm going to go 0 to 15 for my X. And then looking at list 2, I think I'm going to start at 7,000 and go up to 15,000. So I hit my window button, and we said 0 to 15 captures our data, gives a little room. And 7,000 to 15,000 again captures our data, gives a little room on each end. And so now in my y equals, I want to take out things that I've had in here from earlier, and I want to turn my plot on. So I go up here to plot 1 and hit enter. And then when I come back down, I see that's in the dark box. So that is turned on, and I can hit graph. And I had that plot previously set up to the first type of graph and the largest icon there. And so when I look at these data points, they very much look like a straight line. So going back to this, create a graph. So we did that. So we went 0, 15, we went, this is year, 7,000 to 15,000. This is our endangered species. And our data points very much look like a line. So I'm just going to approximate them on my graph. So we started here and something of that nature. So not drawn with any precision, but the big question, what type of function and why? So my answer would be that it is approximately linear. And the why is because data points approximate a line. So we have previously done approximately linear, and so to find this equation, we're going to use our calculator, and we use option number 4, which is the linear regression, which is going to give us the AX plus B, which matches up to MX plus B model. So on my calculator, I go to Stat, and I go over here to Calculate, down to option 4, enter, enter through these. If you want to store the regression, you can do that by hitting the vars button, over to the y vars, enter for function, enter for y1. If you don't want to store it, you just enter through that and ask it to calculate. And so I will have to round off somewhere, but it gives me a regression equation. So back here on my slide, find the equation. And so we have y is equal to 525.93. That was our slope, so that's the x, plus 7953.4. So kind of intimidating stuff, because this slope means that there are 526 approximately additional species that become endangered species each year, because our slope takes the change and divides it out per year. And so we're gaining approximately 526 endangered species per year. It did not ask me to add the line to the graph, but I had stored my equation because I wanted to look at that just to see it. So in my y equals, you see that they put the equation in there, and they put way more 3's than I would have if I typed it, but very close to what we wrote down. And when we graph that, we see that it is an excellent approximation of our data points. And we do see that some of them are just a tick above or a tick below the line. And so it truly is an approximation. It's not exactly hitting the data points, but very, very close, a very good estimate. So back here, what type of function and why? Approximately linear based on the graph. And that's what we're looking for when we don't have constant change and we don't have constant ratios.